Minute Math. When you need help, you use Minute Math.
Hi, I'm Sean Gannon, and this is Minute Math, and today we're learning about distance, rate, time, word problems. So, if I was given this problem, an aircraft carrier made a trip to Guam and back. The trip there took 3 hours, and the trip back took 4 hours. It averaged 6 kilometers per hour on the return trip. Find the average speed of the trip there. Okay, so we have two trips in a sense. The distance is going to be the same, right? The distance to Guam and back, the distance to Guam is the same as the distance back to Guam. So the distance we have really, in that case, if you have, we have going there, and then we're coming back. Okay? Well, since the two distances are the same, all right, then we know, in a sense, we can see it like this, that distance is going to equal our formula for rate times time in both directions, right? There and back. So distance equals rate times time, distance equals rate times time. Distance is the same, so we can set them equal to each other here. So now we have to figure out what the rate and time are for the trip there and the return back. So we're trying to find the average speed on the one there, this R right here. Okay? So on the return trip, they said it averaged 6 kilometers per hour on the return trip, and the trip back took 4 hours. So the return trip took 4 hours. Right? And so we have 6 kilometers an hour times 4 hours. That gives us a total distance to Guam. That's the return trip took. And the trip there, they said, okay, on the way there, it took 3 hours. And notice I'm getting rid of the distance. Don't need that anymore. We don't actually really need to know what that distance is because they're kind of equal to. And the rate on the way there is what we want to find, the average speed on the trip there. So now we have to simplify this. Well, pretty easy, right? We have 6 times 4, right, is 24. And we have 3 times r here, just kind of rearranged it. Divide both sides by 3. And now we have r. Our rate is 24 divided by 3, which is 8. And that's 8 kilometers per hour. And what that is our answer for the average speed of the trip there. A passenger plane made a trip to Las Vegas and back. On the trip there, it flew 432 miles per hour, and on the return trip, it went 480 miles per hour. How long did the trip take there if the return trip took 9 hours? So we kind of have our trip, let's go there and return. So we're on our way there, and our return. All right, going to kind of categorize it like that. We know distance equals rate times time. But one thing we can do, rate times time and rate times time. Now notice, it's the same distance to Las Vegas and back. The trip to Las Vegas is the same distance as the trip back from Las Vegas, right? So the distances will be equal, and essentially on our next step, we're just going to put an equal sign here and eliminate that and set rate times time to be equal to each other for the trip there and the trip back. So on the trip there, they tell us that it flew 432 miles per hour. And it told us on the return trip, it went 480 miles per hour. Okay? Now they said the return trip took 9 hours. And they want to ask us, well, how long did it take the trip to get there? So now we have an equation. That was our goal. And now we have to solve for t, the time it takes to go there to Las Vegas. So multiplying this out, 480 miles per hour times 9 hours, we have 4,320 miles. And then here we have, just bring down that 432 miles per hour times time. Divide by 432. And we get a time of, well, 4,320 divided by 432 is 10 hours. And that is how long the the trip to Las Vegas took. A cattle train left Miami and traveled toward New York. 14 hours later, a diesel train left, traveling at 45 kilometers per hour in an effort to catch up to the cattle train. After traveling for 4 hours, the diesel train finally caught up. What was the cattle train's average speed? Okay. So one thing they tell us here, we have the diesel train, I'm going to call this DT, we're going to call the diesel train here, and we have the cattle train, CT. Their distance, right, the distance that we're going to find for each one is going to be the same total, where they caught up, okay? So they're going to catch up at the same total distance from leaving Miami, traveling toward New York. When they meet, that distance is going to be the same in our calculation here. Okay, so they tell us that after traveling 4 hours, the diesel train caught up to the cattle train. So distance equals our rate times time for both of them. So the diesel train, when it traveled for a total of 4 hours, and it was traveling at 45 kilometers per hour, it traveled the same distance as the cattle train did in that time to catch up to it. Okay, so it only took 4 hours going at 45 miles an hour to cover that same distance. Now the cattle train, they said ran for total, right? Total. So its rate we don't know, but its time. Okay, it was traveling 14 hours before the diesel train left, and then 4 hours later is when they finally met. So its total time traveling was 14 hours plus 4 hours. So now, 4 hours times 45 kilometers per hour is 180 kilometers, right? And that's the distance it traveled, right? 45 times 4 would be 180, and then here we would have R times 14 plus 4, which is good old 18 hours. We have to solve for R, so we divide 18 to both sides. And rearranging, having R come first, 180 divided by 18 is 10, and that's 10 kilometers per hour. And that is how fast the average speed of the cattle train. Josie left the White House and drove toward the recycling plant at an average speed of 40 kilometers per hour. Rob left some time later, driving in the same direction at an average speed of 48 kilometers per hour. After driving 5 hours, Rob caught up with Josie. How long did Josie drive before Rob caught up? Okay. So one thing we know, we have Josie and we have Rob. And we know that distance equals rate times time. And the distance that they both traveled is going to be the same. So for Josie, I'm going to put rate times time like this. Now, we don't really need to know what that distance is. The equations are both the same distance overall, so we can kind of set them, or can set them equal to each other. Okay? So, equal sign here. Okay? We know Rob traveled at some time later, okay, and he traveled 48 kilometers per hour, okay, but after he drove for 5 hours, okay, so Rob left some time later and he drove for 5 hours and caught up with Josie, okay, so after 5 hours of driving, when he left, he only traveled for 5 hours, he caught up to Josie. So we have 5 hours here. He covered that same distance. Sometime later, he eventually traveled for 5 hours. Now, Josie, though, we know traveled 40 kilometers per hour, but we don't know how long she traveled for. That time we don't know. Okay, so now we have to solve for her time, Josie's time that she was traveling at 40 kilometers an hour. Remember, they're catching up to each other. So 48 times 5 is 240. And we have 40 here, 40 times t. We divide both sides by 40 to get t by itself. And our time by itself here, 240 divided by 40 is 6. And that is in hours, times in hours. And so Josie, all right, how long did it take Josie to drive, or how long did Josie drive before Rob caught up? And she drove for 6 hours until Rob caught up. A cargo plane flew to the maintenance facility and back. It took 1 hour less time to get there than it did to get back. The average speed of the trip there was 220 miles per hour. The average speed on the way back was 200 miles per hour. How many hours did the trip there take? Okay, so we have two directions. We have there and back. There and back again. All right, you get that reference? Maybe you don't. We have there and we have back. Okay. Now, one thing we know is distance equals rate times time. But the same distance is traveled to go there as well as coming back. Okay, to that cargo facility. Or cargo plane to the facility, right? Maintenance facility. So that distance, we showed the rate times time there should equal the same rate times time on the way back. Okay, this helps us here. So since they're both equal, we don't really need to know what that distance is. So we can set them equal to each other. Now we have rate times time. Well, the rate there or back was 200 miles per hour. And we don't know necessarily the time it took to get back. But they do tell us on the way there, we traveled 220 miles per hour. And the time, though, now here's the tricky part. The time, they said, it took 1 hour less time to get there than it did back. So if back is written as variable t, the time to get there, that time would be t minus 1. And this overall will be the time it took to get there, and then back being t hours. But now we have an equation with one variable, we can solve for that variable t. Okay? So distribute here, 220 times t is 220t, minus 220 times 1 is 220. And then we just have 200t here. All right? I subtracted 200t to both sides. Make sure you go with your like term. And in the same statement here, I'm going to add 220 to both sides. 220. There we go. These cancel, and 220 minus t minus 200t is a 20t. And that's equal to what's left here. These cancel again, is 220. Divide 20 to both sides, and I'm left with t equals 11 hours. But remember, they said t represents a time back in our equation here. So time back is 11 hours. We know we have one less hour to get there. So we have 11 minus 1, which is, note here, right? 11 minus 1 is 10. So 10 hours is actually the time it took to get there. Callie left school and traveled toward her friend's house at an average speed of 40 kilometers per hour. Matt left 1 hour later and traveled in the opposite direction with an average speed of 50 kilometers per hour. Find the number of hours Matt needs to travel before they are 400 kilometers apart. Okay, so let's get a little visual here. Okay, we have our school. Let's draw a little school here, a little house school, right? Is there a school? Our school, okay? They told Callie left school and traveled toward her friend's house. So she goes this direction, and she's traveling. So her friend's house is somewhere over here. She's traveling 40 kilometers per hour. They also tell us that 1 hour later, Matt left, okay, in the opposite direction from school. So Matt is going this way. So we have Callie, and we have Matt. Matt's traveling at 50 kilometers per hour, okay? But the key thing they said, Callie had already traveled 1 hour. So she traveled a distance of 40 kilometers in that 1 hour. She traveled 40 kilometers before Matt started going in the opposite direction, okay? So that means at this point of time, after 1 hour has occurred, they are 40 kilometers apart, okay? So our overall distance here, our overall distance, all right, since distance equals rate times time, our overall distance, well, is the rate at which they are moving apart, okay? So they're moving apart 50 and 40, so 50 kilometers per hour one direction, 40 the other. Add them together, they're moving at a distance getting apart of 90. Add them, right? Add them, 50 plus 40 is 90. 90 kilometers per hour, okay? Now we have to times that by our time. We don't know how long it will take, okay, how long it will take that. But then we're adding, all right, we're adding the initial distance here of 40 kilometers. So after 1 hour, okay, after 1 hour of Cali travel, they're 40 miles away, so we make 40 kilometers away. So we make sure we add that to it. Okay. Now the key here is the question. T is representing the number of hours Matt needs to travel before they are 400 kilometers apart. So we have already included the 1 hour Cali travels right here, but this T is only representing the time Matt traveled. Okay. So now we have an equation, and well, distance, that's going to be 400. That's the goal, right? So 400 kilometers equals 90 kilometers per hour times t plus 40 kilometers, okay? So now let's go solve for t. We subtract 40 to both sides, and we're left with 360 equals 90 times t. Divide both sides by 90, and we're left with, I'll put it here, t by itself. 360 divided by 90 is 4, so 4 hours. And so it will take Matt 4 hours of driving until Callie and Matt are 400 kilometers apart. Ryan left the Science Museum and drove south. Gabriella left 3 hours later, driving 42 kilometers per hour faster in an effort to catch up to him. After 2 hours, Gabriella finally caught up. Find Ryan's average speed. Okay, so we know distance equals rate times time. Okay, we have the distance for, let's do Gabriella's over here. Okay, and the distance for Gabriella is equal to, right? Well, the rate she's going is 42. They give it to us as 42 kilometers per hour, right? Faster than Ryan. So whatever 42 kilometers an hour plus Ryan's rate, that's our R, times, well, how many hours, okay? After 2 hours of driving, she caught up, okay? Now, that's the distance for Gabrielle. I'm going to put Ryan here. And the distance for Ryan, put it equal the other way. Ryan's rate, we don't know. But Ryan was traveling for 3 hours, all right, and then Gabriella left, and then after 2 hours caught him. So 3 plus 2, 2 plus 3 doesn't really matter the order, together gives us the time Ryan was driving. Hours, okay? Well, we know the distance that the overall for Gabriella and Ryan were the same, so we can kind of make them equal to each other here, and now we have an equation. 2 plus 3 is a 5, so we have 5 times, rewriting this, Ryan's rate, so that 5 times or 10 times fast, and now we have, here I'll put it in here, 42 plus Ryan's rate times 2 hours, okay? Distribute this to both parts. 42 times 2 is 84, plus 2 times RR, Ryan's rate. And then we have 5 times Ryan's rate here. Okay, get our like terms together. We subtracted 2 of Ryan's rates to both sides. 5 minus 2 is 3. 3 Ryan's rates here is equal to 84. Okay? Divide both sides by 3. Remember, that's multiplication here. And we have Ryan's rate, put it right here on the side. 84 divided by 3 is 28. 28 kilometers per hour. And that is how fast, or Ryan's average speed. A submarine left Hawaii 2 hours before an aircraft carrier. The vessels traveled in opposite directions. The aircraft carrier traveled at 25 miles per hour for 9 hours. After this time, the vessels were 280 miles apart. Find the submarine's speed. Okay? So I like to kind of draw a picture. We have Hawaii right here. Hawaii. That's a big I. There we go. Second big I. All right. We have the submarine, so we have Hawaii right here. The submarine traveled in one direction. This is a sub. Okay? Then, all right, aircraft traveled the other direction, right? The other direction here. A little dot here. Other direction. And the aircraft carrier traveled 25 miles per hour. And they told us that it traveled for a total of 9 hours. Okay? So the submarine left 2 hours before the aircraft carrier, and then the aircraft carrier left and traveled 25 miles per hour for 9 hours. After this time, the vessels were 280 miles apart. We have to find the submarine's speed. So getting a little picture here of what's going on, we know distance equals rate times time. So let's go find the distance that the aircraft carrier actually traveled. So the aircraft carrier's distance is 25 times 9. So the distance of the aircraft carrier is 225 miles. And that's how far it traveled at that time. Okay? The submarine, so this is the aircraft, the submarine traveled, the distance of the submarine is, again, rate times time. So the submarine is rate times time. And the distance the submarine traveled, okay, this one's a little, well, tricky. How do we get that distance for the submarine? Well, what we know is that overall we traveled a total, or the two aircraft carrier and submarine were 280 miles apart. So we have 280 miles. And we're going to subtract the distance the aircraft carrier traveled, which was 225 miles. And that should equal the distance the submarine had traveled, which is 55 miles. So we continue that here. 55 miles is the distance the submarine traveled. Okay? And that's equal to our rate times our time. Now, the submarine was traveling 2 hours more than the aircraft carriers. So we have 2 plus 9 here for the time traveled for the submarine. 55 equals R times 2 plus 9 is 11. We now divide both sides by 11. And I'll rearrange this, kind of cut this off here. R is by itself. 55 divided by 11 is 5. That's 5 miles per hour. And that is how fast the submarine speed is. Chelsea left the White House and traveled towards the Capitol at an average speed of 34 kilometers per hour. Jasmine left at the same time and traveled in the opposite direction with an average speed of 65 kilometers per hour. Find the number of hours Jasmine needs to travel before they are 59.4 kilometers apart. Okay? So, we have our White House right here. White House. Okay? And it tells us that they're traveling in opposite directions. So Chelsea left and went towards the Capitol. All right, this is Chelsea. Chelsea, a little space here, unnecessary. Well, that's unnecessary E. And she's traveling 34 kilometers per hour. At the same time, Jasmine left in the opposite direction. So here's our Capitol. Okay? Jasmine goes in the opposite direction. That's Jasmine. Goes in the opposite direction, but she's traveling 65 kilometers per hour. Okay? So we see how many hours they need to travel before they are 59.4 kilometers apart. So our distance is our rate times our time. Our distance we're trying to find is 59.4 kilometers. And here's the tricky part. Since they're traveling in opposite directions, right, the rate at which they are separating from each other is adding both these rates together. 65 plus 34, that's our rate, kilometers per hour, times a total time of t. All right, so now we have a problem. Let's go solve. 59.4 equals 65 plus 34, which is a 99, times t. Divide both sides by 99, and t is now by itself, which is 0.6. So after 0.6, or 59.4 divided by 99 is 0.6. 0.6 hours is how long Jasmine needs to travel before the two of them are 59.4 kilometers apart. Josie left the airport and traveled toward the mountains. Kayla left 2.1 hours later, traveling 35 miles per hour faster in an effort to catch up to him. After 1.2 hours, Kayla finally caught up. Find Josie's average speed. Okay. So we have two formulas we're going to kind of put together here. Okay. We have the distance of Josie. Okay. Or yeah, let's do Josie's first. Or actually, let's do Kayla's first. So distance for Kayla, this is Kayla, is equal to the rate of Kayla's times Kayla's time. And the distance for Josie, put it right here, for Josie, flip it around the other way, is the rate for Josie times the time for Josie, okay? And we know the overall distance between the two, dk and dj, will be the same. So, this is Josie. So we can eventually, we're going to set them just equal to each other. Now, how can we write this? Because they're written in terms, or they're explained in terms of each other. So Kayla's rate, they said Kayla was traveling 35 miles per hour faster than Josie. So her rate is 35 plus the rate of Josie's, R times J. And she traveled for a total, okay, after 1.2 hours. So she traveled 1.2 hours before she caught up to him. Josie, though, on the other hand, we don't know Josie's rate, but Josie traveled a total of 2.1 hours plus the 1. So he was traveling 2.1 hours, and then Kayla left and then caught up to him, plus that 1.2 hours that she drove. I'm going to put a plus sign there, and of course I didn't give myself enough room, so I rewrite that. So write it as one statement. Here we have 2.1 plus 1.2 hours. Okay, so he was traveling 2.1 hours, then Kayla left, and after 1.2 hours, she caught them. That's when they covered the same ground. So now we want to solve for R of J, the rate at which Josie was traveling, or his speed, right? So we need to add these two up. So we have R times J. 2.1 plus 1.2 is, 3.3, equals, okay, here we distribute the 1.2 hours. 35 times 1.2 is 42, plus 1.2 times Rj, or R sub j is 1.2 Rj. Okay, so rewriting this, so it kind of matches up with variables. 3.3 Rj equals 42, plus 1.2 Rj. I'm going to subtract a 1.2 times Rj to both sides here. And 3.3 minus 1.2 comes out to be a 2.1 Rj. That's equal to 42 here. Then I need to divide by a 2.1 to both sides, and that 2.1's cancel, giving me Rj by itself, the rate at which Josie's traveling, and 42 divided by 2.1 is 20. So we have 20 miles per hour, And that is the rate at which Josie's average speed.
Minute Math. When you need help, you use Minute Math. Minute Math. Minute Math. When you need help, you use Minute Math. MinuteMathTutor.com.